Hi everybody. So for this video I want to do some more complicated examples of finding limits of sequences. So in the last video we talked about the tower of power, as I like to call it. Right? So if you have a fraction and you just have something in the top and something in the bottom, then all you have to do is figure out where the power lies, right? Which which has more power, the top or the bottom. Right? And you look and you see where the most powerful function is, which one grows the fastest, essentially is what I mean by most powerful. And then they'll tell you whether the bottom wins and the whole thing goes to zero, the top wins, the whole thing goes off to infinity, or maybe there's a tie and we look at the coefficients of the most powerful thing in the top and the bottom. That was the subject of our last video. For now, I want to do a couple of examples of things that are trickier. So here's an example. We want to find the limit of this sequence. And notice there's big parentheses, and we use parentheses a lot in the last limit, in the in the last video. And so you might think at first glance that the sequence is 1 plus 1 over k, but actually see the k in the exponent here, which is the point. So if I were going to write this with parentheses, I put parentheses around the whole thing if I were going to call this a sequence. But I usually won't put parentheses if I'm writing a limit in front of it. So I have the limit of, again, this is what the terms of my sequence look like. Parentheses 1 plus 1 over k, all raised to the kth power. So again, we have k's raised to the kth power. So there's an obvious wrong way to do this, right? The wrong way to do this problem is to say, well, look, when k gets really big, the power right here in this fraction is all in the denominator. So this fraction, 1 over k, of course, goes to 0. So this means 1 plus 0, the parentheses then would all be going to 1. And then 1 to the kth power, that ought to just be 1. So the answer should be 1, except it's not. It's way not. And the reason is, if you even rewind the video for a second and listen to what I just did, I talked about taking this part, the fraction, letting it do its thing, right? So the limit here would go to 0, then I add it to the 1, then I worry about this k. But you see, the k's are both going off to infinity together. I can't just take this k inside the parentheses and let it go off to infinity and ignore the one outside, because they're the same k. So I can't do them separately. I have to worry about both of them at the same time. That means this is a much more complicated kind of question. It's not just a fraction that I can just look at and see what the answer is. This is a job for L'Hopital's rule. So if you remember L'Hopital's rule from Calculus 1, that showed up when we had limits, well, that looked like infinity over infinity or 0 over 0. Or there were some special kinds where there was like 1 to the infinity power. That's what we have going on here. So the first thing we need to do in order to be able to work this kind of problem is we need to commit algebra. There's a great column by George Will where he talked about committing algebra in one column. So I love that phrase. What we're going to do is like algebra is a felony, right? So what we're going to do is change the problem up a little bit by taking the logs. I'm going to take ln on both sides. Okay? Well, there's only one side so far. Right? So where's the other side? Well, we'll see in just a second. So I'm going to take the log of this. Notice I've changed the problem. So I'll come back to this in a second, what I just said about the other side. I'm going to have to do something to fix the fact that I'm changing the problem at the end, right? So don't forget the fact that I'm not solving the original problem anymore. I've changed it. But I've changed it in a good way because I've got algebra that can help me now. Log of stuff raised to a power. Well, if you remember, this is going to, maybe it looks like a derivative almost, because what I'm going to do, although it's not, this is just algebra. If I have log and a power right here, remember I can take that kth power and bring it down in the front, and that's just algebra. Okay? This is just the magic of logarithms. So you see my little brown k there that I can bring down in front and make it k log of 1 plus 1 over k. Okay, so remember I said L'Hopital's rule is great for things that look like a fraction that's 0 over 0 or infinity over infinity. How do I make this look like that? Well, I need to get a fraction somehow, so I do one more little bit of algebra. I'm going to take that k that's in front of the log, and I'm actually going to move it to the denominator but make it 1 over k. And so it's easy to see, right, how you could go from the bottom example here back up to the top, right? Because the bottom would flip and the k would come here. So why would I make it look worse by doing this to it? Well, if you look at the fraction I finally have down here at the bottom, when k gets really big, this k, right, 1 over k, I should say, will go to 0. Over here, this 1 over k will go to 0, so I'll have the log of 1. Now, if you remember logs, the log of 1 is 0. So this looks like a 0 in the top over a 0 in the bottom, and this is where L'Hopital's rule goes to a phone booth really quick, changes into its cape and mask, and comes in. It's a job for L'Hopital's rule. Okay, so what we've done here is taken the log that let us separate off the two k's. So now I've got a k in the denominator and a k that's in the numerator, and I can worry about the two separately. Okay? And that's what L'Hopital's rule will let us do here. Okay, well, there's a little bit to worry about, a tiny bit here with L'Hopital's rule, because technically L'Hopital's rule requires us to take a derivative, right? Remember, we take the derivative of the top, we take the derivative of the bottom. It's not the quotient rule or anything like that. It's just derivative of the top divided by derivative of the bottom, and we see what happens to that limit. Okay, technically, when you take the derivative of a function, the function has to be differentiable. In other words, it has to have a derivative. And part of that is the function had to be continuous. And if you remember in the last video, when we were graphing sequences, we just graphed a bunch of dots. It was not a continuous function. So this is something that's a slight pet peeve of mine. And the truth is, you can get the right answer by writing down the wrong thing, right? Differently than I'm about to write it down. But if you write down the wrong thing, I will count off for it on the exam. So remember, the exam is not about getting the right answer, right? It's one of the hardest things for people to understand when they get to college and they're doing college level mathematics. The exam is not about getting the right answer. The exam is about convincing me that you know what you're doing. Okay? It's about showing me that you understand the problem. So what I'm going to do here is I'm going to insist that we change this k to an x. Now again, this looks like, what's he doing? Why is he being so silly? This is stupid. Okay, yeah, I give you some of that. I mean, this doesn't actually change the way the problem works. But the reason I'm changing the k's to the x's is to emphasize this. What we're doing is we're not actually applying L'Hopital's rule to the sequence. What we're doing is we're replacing the sequence with a function, right, defined exactly the same way the sequence was. So if I were to graph this new fraction that's here on the left with x's, I treat x as a continuous variable, right? Not just 1, 2, 3, 4, but x could be any real number, okay? Or positive real number, say. Then what I would get is a graph that was, smooth, um, connected, continuous, and in fact differentiable. So I could use L'Hopital's rule for it. Remember, when I graph a sequence, I just get a bunch of dots, and you can't actually take the derivative of a bunch of dots. So what I do is I replace them all with x's. Now I've got a function that's differentiable. I can take the derivative of a function. And again, you get the right answer by ignoring what I'm about to say, but you'll lose points on the exam because I need to know that you know that L'Hopital's rule works when you have functions, not when you have sequences, because sequences aren't differentiable. Okay, the way L'Hopital's rule should work is I take the derivative of the top, then the derivative in the bottom, and I keep the fraction, derivative of the top divided by derivative of the bottom. So what's the derivative of the bottom? Well, 1 over x, if I'm going to take its derivative, do a little algebra here, let's make that x to the minus 1 power. And then the derivative would be minus, to bring down the exponent, x to the negative 2 power. Now, it may be that you're a little rusty on derivatives because we spend a lot of time doing integrals. So if that's a little rusty, right, if you see 1 over x and you immediately want to call that log because we're used to doing integrals, that's completely understandable. But be careful when you're working these problems to remember that, oh wait, I'm doing derivatives. So remember, this is 1 over x, that's x to the minus 1 power. So I bring down the minus 1 in front of the x, subtract 1 from the exponent. So that's negative x to the negative 2. Now the top's a little more complicated because I got log of a bunch of stuff. But the good thing is the chain rule comes to the rescue here. So log of a bunch of stuff, if I take its derivative, I get 1 over the bunch of stuff, right? Then from the chain rule, I have to take the derivative of all the stuff. But that's not so bad because the derivative of 1 will just be 0. The derivative of 1 over x, oh, I just did that, right? 1 over x, I'll treat that as x to the negative 1. So its derivative becomes the same, negative x to the negative 2 we had before. Oh, that's awesome, because now this negative x to the negative 2 cancels off with this other negative x to the negative 2. And I'm left with just the limit as x goes to infinity of 1 over the stuff, 1 plus 1 over x. And that's a limit that's easy to do now. This was the whole point of L'Hopital's rule, is you had a 0 over 0 or an infinity over infinity limit. You take the derivative of the top over the derivative of the bottom, and hopefully you get something you can actually do now. And now we have something we can do, because when x gets really big, 1 over x will get close to 0. 1 plus 0 is just 1. This whole thing in the denominator, the stuff, is just 1. The numerator is just 1. So this whole limit is just 1. So, wait a minute, I thought you said that the answer wasn't 1 a few minutes ago, and I was talking about the wrong way to do this problem. Well, the answer is not 1, because remember, we changed the problem by taking the log. Right? The original problem was this one in blue. Okay? It was 1 plus 1 over k all raised to the kth power. The problem we just solved was log of that. And when we took the log, right, and then we worked the problem, we got 1. So what we really have here is log of what we wanted is 1. Oh, okay. So how do I solve for what I want? Right? If I've got an equation that says log of what I want equals 1, well, the way you get rid of a log is you exponentiate. In other words, you e both sides, right? So e to the x and log undo each other. So log of what we want equals 1 means what we want is e to the first power. So the answer wasn't 1 after all. The answer to this original problem we started with was e. Wow, that's really cool. In fact, just as a quick aside here, this is one reason why some books called late transcendental books will wait until right now to ever talk about e to the x. Right? They do all of the sort of derivatives and integrals and stuff, and they only ever use polynomials. They don't do e to the x or log or any of it, because they want to get here where we have a good definition of what e actually is. You could define e to be this limit and go from there. I don't like doing that because, I mean, everybody's already seen e's and logs and sines and cosines and all that sort of stuff in high school. The cat's already out of the bag, right? Everybody already sort of knows the mystery of at least that e and log exist. So we may as well just do them from the beginning. Okay, another question along the same lines. K raised to the 1 over k power. Well, again, the trick here is to commit algebra. Right? We take the log of this because we have k's raised to powers that have k's in them. The base and the exponent both have k's in them. So we can't just do it, simple-mindedly, right? And say that the 1 over k in the exponent goes to 0 and anything to the 0 power should be 1. That argument doesn't work because I got k's in the base and the k's in the exponent. So we take log of both sides, ln of k to the 1 over k. Well, this actually is going to work out much quicker than the last example did, because when I bring that 1 over k down in front of the log, well, it's a lot easier to get a fraction, right? The 1 over k that I bring down, I can rewrite that really easily as log of k over k. So it's not quite as forced as having to take a k and stick it in the denominator and make it 1 over k. The algebra is much more obvious here how we would do it. So once I take the log, I get log of k over k. And now what does that limit be? What should this be? Well, it's 0 by the tower of power, because who's bigger, log or k? Well, the log of k is the puny one. K has the more power, so the bottom wins. The whole thing goes to 0. But rather than just say that, I mean, on an exam you could say that, that'd be perfectly fine. But let's practice our L'Hopital's rule for one more example, just because that's something that usually people have forgotten, and it would help to do another L'Hopital's rule example, even though the answer, of course, is going to turn out to be 0 here. So first thing is to turn all those k's into x's. Again, I'm going to make a big deal out of this because I'll count off on the exam. You have to turn the k's into x's, and recognize that we're not using L'Hopital's rule on a sequence. We're using L'Hopital's rule on the differentiable function log of x over x. Why does L'Hopital's rule work here? Well, when x goes to infinity, log of x is infinity in the denominator, so it's an infinity over infinity kind of limit. But when I take the derivative in the top, the derivative of log of x will just be 1 over x. The derivative of the x in the denominator is just 1. So I get 1 over x over 1 once I've done the derivatives. That's really easy because, of course, 1 over x goes to 0. 0 over 1, just 0. So we knew that from the Tower of Power already, but going through and seeing L'Hopital's rule again was probably worth it if your L'Hopital's rule is a little rusty. So the gist was we took log of the problem we wanted. We were able to see that that limit was 0. But again, that's not the answer to the question we wanted. The question we wanted was k to the 1 over k, not log of that. So just like we had before, log of what we wanted was 0. So what we want is e to the 0. We have to solve for what we want, right, in this equation. Of course, e to the 0 is just 1. So the limit as k goes to infinity of k to the 1 over k, that's 1. Well, so this brings us to another page, and this is a list of 3 important things to know. So these are facts that you'll want to file away, right, somewhere in the back of your head, so that when we see them later, you can just pull them out and use them. So the first is the first example we had. The parentheses 1 plus 1 over k all raised to the kth power. That sequence goes to e. And there'll be places where you don't want to have to redo what we just did in that example. From now on, if you see just that, exactly like that, you'll know the answer is just E. Right? Now, if you see a variation of this problem, and you will in the homework, where instead of a K right here where I'm moving my pointer around, maybe there was a 3 here, and up here instead of a K, maybe there's a 6K here, right? Then you have to go through and you have to do the whole L'Hopital rule again to see, because it's a different question. But if you see exactly this question, then you know the answer is going to be E. And that's an important thing to file away because there'll be examples later when we get into series where we'll just need to know that. Right? That'll be a small part of a bigger problem. The same thing, the kth root of k, right? Or k to the 1 over k power. That's the kth root of k. That limit's just 1. And the kth root of a positive number is also in the limit just going to give us 1. Right? So like the kth root of 7 or the kth root of 15, well, that sequence will converge to 1. That'll be really useful for some stuff we're going to see later in we talk about series because we will have series that we need to do something to, and the answer will boil down to looking at a sequence. And if the sequence we have is one of these 3, then that we already know the answer to.